Good morning. Welcome back. I noticed many of you were working on the assignment yesterday. Many of you were wiser and worked on it earlier. But hopefully most of you, if not all of you, are finished with it. And I wanted to go back for a minute to what is supposed to be the main point of that assignment, and that is the necessity of bias. So I want to show you how I would have solved this assignment kind of in my head or on the board using a mini example. And the mini example, because I can't write too much on the board and it won't fit anyway, I'll just use 4 possible inputs. Okay? So let's say the problem is my favorite colors I like. The concept is and the input space consists of only 4 colors: red, blue, green, and yellow. I can even call it primary colors I like. Primary colors I like, so there are only 4 primary colors. Input space size is 4. What many people found confusing is that sometimes the input space itself consists of a combination of features, a combination of attributes. And if the attributes are binary, and there are k of them, then the input space size is 2 to the k. Right? But that's separate from the fact that the concept space size is always 2 to the input space size. So the concept space size is 2 to the input space size, which is 16. I talked a lot about different ways of visualizing and thinking about binary functions. You can think about them as functions that produce 0 or 1. You can think about them as subsets of the input space, or you can think about them as bit vectors. And most useful here is to think about them as bit vectors. So if I list here all the inputs, there are only 4 of them, right? There's red, blue, green, and yellow. And here I can list explicitly all the functions. So one function, which I'll call f sub 0, says I don't like red, I don't like blue, I don't like green, I don't like yellow. That's one function, that's one concept, one potential answer. I'll do another one, I'll call it f1, f sub 1, I only like yellow. And then this one, I only like green. And this one, I like both yellow and green, but none of the others. I'll put a little line here. And now I'll fill this really quickly. 0, 0, 0, 0. Put a big line here. 1, 1, 1, 1. 1, 1, 1, 1. And this is 1, 1, 1, 1. 0, 0, 0, 0. 1, 1, 1, 1. And this is 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. And this is 0, 1, 0, 1. 0, 1, 0, 1. 0, 1, 0, 1. Hopefully most of you have done exactly that in your program. Maybe you came up with a different representation, that's fine. This goes all the way to F15. Here's F sub 7. Here's F sub 8. There's an explicit visualization of all possible ways of mapping any one of 4 elements into a yes or a no. That's just the beginning, the background. Now comes the learning part. We're going to learn in this space, so we're going to assume that H is the same as C. No inductive bias. And learning in this space will consist of seeing some training examples with labels and trying to infer what the labels are for the other unseen examples. Since there are only 4 possible training examples, because the space is so small, we will learn from, let's say, 2 or 3, however many you want. So we're going to start with 1 training example and the label. And you can give me whichever training example you want and whichever label you want. The result will be the same. So which training example do you want to learn from?
Red 1, blue 0.
Red.
1, 2, 0.
I'm sorry?
Red, I like red, I don't like blue.
You like red, you don't like blue. So let's start with we like red. This is a training example, so we'll call it X1, X1 and Y1, right? X1 and Y1 is red. And yes, I like it. 1. Explicit enumeration means you go over all of the functions and you check to see if they're consistent with this training example or not. And those that are not consistent, you throw out of your space. So you're shrinking your version space. If red equals 1, that means that in this row, this function must have a 1. That means that all of these are consistent, but all of these are not. So in one fell swoop, we eliminate this entire part of the space. We cut the space in half from 16 to 8. That's pretty good. We can try to learn in this space. We can try to guess what we can use the remaining members of the version space to vote on any of the other unseen examples. For example, how would they vote on yellow? Half and half. How would they vote on green? How would they vote on blue? How much have we learned? Nothing. All right, let's try another example. Let me do green now. X2, Y2 is green and 0. That means only continue to consider functions that in this row have a 0 and cross out those that have a 1. That means we cross out these and we cross out this. How would you vote on blue? Still half and half. Can you see why it will always be half and half? Okay? That was the purpose of this exercise. It means you cannot learn, you cannot generalize from examples you've seen to examples you have not seen if every possibility is there to start with. Another way of saying it is there's no crosstalk between the examples. The value of green, whether you like it or not, has no bearing, no relationship, no information about the value of yellow or any of the other colors. This is true regardless of what the input space is or how big it is. It's a function of the fact that we have no inductive bias here. This is also true for real functions, not toy binary examples. It's true for numerical functions. In numerical function, the space of functions is infinite, if the output is infinite, or even if it's countably or uncountably infinite. But the principle is the same. Knowing about the value of the function on some points tells you nothing about the value of the function at other points unless you make prior inductive assumptions. The common assumption we make with simple numerical functions is that they are continuous, more or less, or smooth sometimes, or of low curvature. And these are very strong assumptions. Questions? Yeah?
So in this case, I just most beautiful, but in this case, the concept, the input space is 4 because these are just independent values.
Right.
But in some of the previous examples, the input space was 2 to the number of inputs because 2 to the number of attributes.
Right.
Because there are like the answer depends on conjunction or like some sort of function between the attributes. Is that right?
That is correct. So you're pointing out that in this case, I deliberately chose inputs that are categorical. They have nothing to do with each other. But in the other examples, we had the inputs themselves consisted of a combination of attributes. And if there are k attributes, then there would be 2 to the k inputs if the attributes are binary. Yeah. And that's a source of confusion. But it's important to keep it separate. The mapping from number of attributes to number of possible inputs is exponential. The mapping from number of inputs to number of possible concepts is also exponential. Yeah?
So I'm still kind of confused, like why you say the input space is 4 here. So for example, if we have like red 1, like blue 1, green 1, yellow 1, and red 0, blue 1, is it considered as like 2 different inputs?
Is it considered what?
As 2 different.
So the question is, why am I saying that the input space is of size 4? And if we had 2 separate examples of red 1, blue 1, green 1, and yellow 1, or red 1, blue 1, green 1, and yellow 0, are they considered the same input? And the answer is they're not the same input. By input, we mean one of these, without the label. What you were enumerating as examples are examples of functions, not of inputs. A function is specified by the value it assigns to every possible input. Go ahead.
But in the situation of like where input space is equal to 2 to the k, I think it's also like you have like this attribute, and you're like finding a combination of what could be possible.
You're right. There is a similarity between inputs consisting of binary attributes and functions consisting of binary values to every input. But it's not the same thing. The reason I gave this example is to emphasize that the inputs do not have to be a combination of attributes, although often they are. And the attributes don't have to be binary. So by input space, I mean the space of all possible distinct inputs without their values, without the function value on them. The input space consists before you consider what concepts you're interested in. Any other comments or questions? Okay, so let's go back to information theory. To remind you, our motivation is to move from viewing machine learning as function approximation or function learning to viewing it as reducing uncertainty or using the input to reduce the uncertainty in the output. Here we have in mind a mapping from x to y, say. X is some input, y is some output. And we're trying to find that function. What we have here is a mapping from x to some distribution over y. I'll call it p of y given x. And we want to minimize the uncertainty remaining in this distribution. In the extreme case, when the distribution is completely peaked in just one point, that means there will be no uncertainty left. And that would be the same as finding the value of y. But in the more general case, we may not expect that our uncertainty would go down to 0. We would have some uncertainty about y before we saw x. And seeing x and doing something with this will allow us to reduce that uncertainty. And we consider that the more general way of doing machine learning. At least I consider that the most general way of doing machine learning. So we started quantifying what we mean by uncertainty in y. I'll go back to that, but I want you to keep in mind the big picture of why we're doing all of that. Why are we bringing information theory here? So we defined information and we also called it surprise. With regard to some event, E, we define it as log base 2 of 1 over the probability that we assigned, that the subjective probability that you or any one of us assigned to the event E, and that subjectivity is captured by this function Q, which is a bona fide distribution, probability distribution, but it may be different for you than for you. Okay? So it is a probability distribution, but it's determined by whatever you believe about the world. So it's subjective. It is additive. I think I wrote for you the chain rule of information. You take an event, you break it down as a sequence of events. Right? And I also showed you here that you can condition it on events. So you can have E2 conditioned on E1, and we'll have here E2 conditioned on E1. And this additivity allows us to calculate information content of large amounts of input under some very simplifying assumptions. For example, if we assume that every pixel is independent of every other pixel, and we assume a uniform distribution of values over pixels, we can calculate the total information content of any image consisting of pixels. What values can information take? I think we went this far as saying non-negative numbers can achieve 0, it can achieve infinity if you are foolish enough to expect that something has a 0 probability of happening and it happens. Okay, next I want to define an average surprise given an observer, that's you, and a sequence of events. E1 through En. Average surprise of the observer would be 1 over n, sum of the surprise of the observer for each one of them. Now, if I assume that they're independent of each other, I can just close this parentheses. If I don't want to assume that they're independent of each other, then I can do conditions on all the events that happened before. And I can write this, assuming independence. This would be 1 over n, sum of log 1 over q of ei. This is an average surprise. I sometimes use the word average and I sometimes use the word expectation. Are they the same thing? What's the difference between average and expectation? We're not sure? They're not the same thing. Average is over a set of elements. Expectation is over a distribution. You can think of expectation as a weighted average, weighted by the distribution. But average is a statistic. It's a function of the data. Expectation is a function of a probability distribution, not of the data. Sadly, people use the word mean to mean either. So I will try to stay away from the word mean and use either average or expectation to make it clear if I'm talking about a function of the data, of some collection of data elements, just sum them and divide by their number, or I'm talking about expectation, which is relative to some probability distribution. Right now I'm talking about average. Now, until now I looked from a subjective point of view of someone who has some belief Q about how likely different events are. But now let me pull back and look from an objective point of view. Suppose these these events actually came from some real objective distribution P. I'll write it like this. E is our random variable, actually of uppercase, because random variables are in uppercase. E are some events that are drawn from a distribution, which I will call P, with potentially some parameters, which I'll forget about for now. But let's just say, call it P. These are different kind of beasts. This is an objective distribution. This is the theoretical world we're considering, whereas this is the real world where people have subjective beliefs that may or may not be true. Now, in this world where I know the truth, I'm going to ask, what is the expected value of the surprise of this poor fellow over there who doesn't know the truth? Expected surprise of Mr. or Ms. Q on seeing events from P. You understand what I'm trying to calculate?
What is MX, sorry?
MX is either Mr. or Mrs. I didn't want to be gender biased. So, student Q. Make sure you get these two worlds. There's a subjective world of the person who only knows what they believe about the world. And then there's objective world. You can think about it as God or whoever set up the problem, who knows the truth. This person can only calculate their average surprise because they are exposed to examples from the data and they know what they believe was the probability of each one of them, and they calculate 1 over log of 1 over the probability of whatever they observed, and they average that. Simple. This person or entity can actually calculate a theoretical quantity specific to the belief system of this person, which is they can calculate the expected value of their surprise. They're no longer calculating a average. They're summing over all possible events. And they're calculating the surprise of student Q with regard to these events. But how much are they weighing each one? Expectation of this quantity, so this is the expectation, expected value of Q, I'm sorry, of I sub Q of E. And the expected value is with regard to the truth, which is P. So they're weighing it here by P of E. I'd like you to spend a minute appreciating the difference between this thing and this thing. They look very similar. They're both about somehow averaging or combining surprises. Surprise with regard to the same function Q. But the way they're combined is very different. Here is based on a sample, and it's the sample average. Here, they are based on a theoretical distribution, and they are weighed by the distribution. This is a sample average, this is an expectation. Do they lead to the same answer?
We've got enough samples.
I'm sorry.
You have enough samples of what you know to what you're.
If you have enough samples, so as the sample size grows, you expect that the sample average will converge to the true expectation. And that is true. So I can draw a line that will only hold for the current alignment of the boards as n goes to infinity. But for any finite sample, you don't expect them to be necessarily the same. But expect this to be kind of an approximation, a sample-based approximation of this true quantity. This quantity can be calculated exactly, assuming you can take the summation here over all possible events. One other thing I want to draw your attention to is that the summations are of a different nature. We call this summation by type. And we call this summation by token. When you sum by token, some of the elements in this set might be identical. They might occur multiple times. You flipped a coin, there are only two possible outcomes, and you flipped it 20 times, you're going to get many tails and many heads. You flip the die, you toss a die, there are 6 possible outcomes, but you could have a sequence of hundreds of die tosses. So some event types will occur multiple times. That's okay in a summation by token. Tokens are occurrences. Types are the different types of events that can happen. In the case of a coin, there are only 2. In the case of a die, there are only 6, and so forth. So you see here, I didn't use an index like I just said summation over all event types. Different kind of summation. Question?
Using an example of dice, what would be the real meaning of I, E, Q, and P in this two?
Great question. Asking with the example of the die, what would be the meaning of all these things? So the event space, the space of possible events, is 6 outcomes. You toss the die, and you see what face it comes up on. So there are only 6 values. You can number them 1 through 6, or A through F, or whatever. What would be the P and the Q will depend. Is it a fair die? If it's a fair die, then P would be 1/6 for each one of the possible outcomes. What would Q be? That would depend not on whether the die is fair, but on whether the person believes that it's fair. If the person believes it's not fair, then Q will not be uniform 1/6 for everybody. And vice versa. The person might believe it's fair, but may actually not be fair. So P and Q would each be a distribution over 6 values. And they may not be the same distribution. One more thing, there's only one P in any one case, but there could be many Qs. Because P is objective. It's the truth. We may or may not know it. When I stand on this side of the board, I pretend that I know it. When I stand on the other side, I pretend that I don't. But there is only one. Q, on the other hand, every person could have their own Q. Every person is going to be surprised to a different extent. And therefore, every person is going to get different amount of information and learn differently, depending on their starting beliefs. All right, this thing is called cross-entropy. From the distribution P to the distribution Q. I say from, to, and it's important. The order of this thing is important. If you flip, this is not symmetric with its arguments. If you flip these two, you have to flip them here and you don't get the same answer. What are the units of cross-entropy? Cross-entropy is an expectation of information or expectation of surprise. What are the units of surprise or information? Bits. Expectation of something has the same units as the something itself. So this is expressed in bits. Let's give it a cross-entropy. I'll call it CH from P to Q. When I write P and Q here, I mean the entire distribution P and the entire distribution Q. They are distributions over the same set of events. I'll put a little bar here to remind you that I'm not talking about a single value. I'm talking about a whole distribution, which in the case of a space of finite size is just an array of that size. So this is measured in bits. What can I say about the range of values that cross-entropy can take? Can cross-entropy be negative? No, why not? What can you say about the relationship between the value of an expectation of something and the value of that something? I'm talking here about numerical somethings, numerical random variables. If you have a numerical random variable like information, and you now talk about the expectation of that information, expectation under some function p. The value of the expectation must be within the range of the value of the original variable. If you're taking an expectation is a weighted average of sort. If you're taking weighted average, you cannot go outside the range. So since information cannot be negative, its expectation cannot be negative. So we will have at least a 0 here. Can cross-entropy be 0? Is this justified? What do you think would be the extreme case where cross-entropy is at its lowest? Remember its meaning. Its meaning is the expected surprise of a person who holds some beliefs when they see events in the real world. Yeah?
So the person is not surprised at anything.
It would require that the person is not surprised at anything, which means it requires that they know in advance what's going to happen. Can that happen? Yeah, if I have a coin and I know that it has a probability of 100% of landing on head, maybe because it has 2 heads, and I keep flipping it, and I keep getting hits, and I said, yeah, yeah, I'm never surprised. Okay? So that's the only case. This is the extreme degenerate case. That's the only case with cross entropy would be 0. What about, can it go up to infinity? Can it be infinite, or is it bounded? Yeah?
I have a question. So what is the value of Q of E? Like, so could Q of E ever be 0 or infinity?
Can Q of E ever be 0 or infinity? Infinity, no. 0, yes. Q is a probability distribution. Probability distributions over a set of mutually exclusive outcomes can assign 0 to some of them. Q could be 0 for some values. P could be 0 for some values. Could be the same values, could be different values. Infinity, no, because Q over all possible events must sum to 1. Yeah?
What is the difference between P and Q? Both are probability distributions.
Both are probability distributions. P is the correct probability distribution, the one from which the events are really drawn, the one from which events come. Q is your subjective belief about what the probabilities are. Okay, the answer is yes, it could be infinity. And that would happen if and only if there exists some E such that, being mathematical here, such that P of E is greater than 0 and Q of E is 0. When will it happen? When one of these components blows up, becomes infinity. When will one of these components be infinity? When there's an E that makes this non-zero, but makes this 0. In other words, when something that the subjective observer thought was not possible, actually is possible. It doesn't have to happen. We're not talking here about actually drawing samples. That happened in this world. We're doing a theoretical calculation, we as gods who knows P, doing a theoretical calculation of the expected value of the person over there. As long as there is an event that the person over there thinks has probability 0, but we know it does not, this will cause this to blow up. All right, now let's think about a very lucky or a wise person who happens to get, let's think of the person who sits here, or the entity who sits here who knows P. And let's ask, what is the average surprise of the person who knows the truth, who knows P? This is the expected surprise of someone who believes that the world behaves according to Q. But the world really behaves according to P. What about the person who knows how the world behaves? From their point of view, maybe they also think of themselves as Q, but they happen to be right. Okay? Or maybe they know that they're right. It doesn't matter, one of them. So expected surprise of someone who knows P. That means their Q is P. This would be written as expectation according to P of the surprise according to P of E. So here we have P and Q. Here we have P and P. The sum over E of P of E times log of 1 over P of E. See, here it's Q, here it's P. This is a special case of cross-entropy from P to itself. Cross-entropy from P to itself is also called self-entropy. Or simply entropy. And we can also write it as H of P. So entropy, or cross-entropy, can be thought of as a special case entropy or self-entropy can be thought of as a special case of cross-entropy where the two distributions are the same. Let's make sure we keep track of what all these things mean. This means the average surprise. Events always come from some distribution P. This is the average surprise, the expected surprise of someone who believes something Q, and this is the expected surprise of someone who knows the truth to be P. It doesn't matter whether they believe they're right or not. The only thing that matters is, are they right or not? Now let me give you a fundamental inequality. For any distribution P and distribution Q over any space, given a space for any distribution P over it and any two distributions over it, if you compare the true entropy with the cross entropy, what could you say? Anybody wants to guess? What's the relationship between these entities? Yeah? Cross-entropy probably will be bigger. In fact, cross-entropy is guaranteed to be bigger or equal. And the equality holds if and only if P and Q are the same. Equality if and only if P is identical to Q. As long as P and Q are two different distributions, and they can differ even by a little bit, there's strict inequality there. One way to say it is that as soon as Q changed from P to something else, it becomes strictly bigger. What is our interpretation? We're talking about expected surprise. He who knows the truth is least surprised. On average. Remember, this is an expectation. Is least surprised on average. The expected surprise for the next event, the expectation of their surprise, is lowest. It could be that the next event would actually surprise them more. But on average, either as an expectation calculation or the long-term average of many, many samples, many, many events, they will be least surprised. He, she, who knows the truth is least surprised. Now this is worth expanding on a little bit. First of all, what do we mean by the truth? We do not mean that the person knows what's going to happen next. What we do mean is that the person knows the stochastic process that generates what's going to happen next. It knows the rules, the stochastic rules, the probabilistic rules that decide what happens next. So in the case of a coin, I may know that this coin has a 0.6 probability of generating head and 0.4 of tail. And I also know that the flips are independent. That's everything I can know about the coin. It doesn't mean I know what will come out next. Okay? That's the important distinction. To know the truth in this context means to know the true model or the true process. We're assuming that there's some inherent stochasticity, inherent randomness in the world, but that it is possible for us to learn these stochastic rules, these stochastic models. And if we learn these models and we learn them completely correctly, then our average surprise on seeing events is still not going to be 0, because the world is stochastic. But it's going to be lower than the surprise of somebody else who didn't learn them well, or didn't learn them as accurately as we did. So we can actually make progress in small amounts. We can become very, very closer and closer to more accurate. It doesn't mean we're going to head towards zero surprise. There's a lower bound on surprise, which is given by the entropy of the source. So we'll write it here. This is a lower bound on average surprise, or expected surprise, by anyone. You can say that the entropy of a source is the inherent uncertainty, the irreducible uncertainty associated with that source of events. And cross entropy is the actual surprise, or the actual uncertainty experienced by someone who may or may not know the true distribution, may or may not know the truth. I want to write it in a slightly different form that is also extremely useful. Suppose you're trying to learn the distribution P, and you're doing it with a set of distributions that you're many models Q. So Q, I called it a subjective belief. I can also call it a model. When you create a model, a fancy-schmancy, deep learning model, that's a Q. Okay? You're considering many Qs. There's only one P, but you don't know it. You're considering many Qs, and you ask yourself, which one gives you the lowest value? Which one is the best model in the sense that it minimizes your expected surprise on future events, minimizes your uncertainty with regard to future events? So now you're searching the space of all possible Qs. Okay? What this says is that the answer is P. So if you think of this as a function of Q, although it could be in a very high dimensional space, it is a function that has a unique minimum, and that minimum is achieved at the point Q equals P. So the philosophical take-home message is that even stochastic uncertain events or phenomena have a uniquely optimal solution, in the sense that you can strive to eliminate the uncertainty that comes from not knowing that the true model. Once you settled, hopefully, on the true model, you cannot eliminate the uncertainty anymore. You have to live with the remaining uncertainty. Again, an example of a coin. I hold the coin in my hand. I don't know the probability of head. It could be anything from 0 to 1, somewhere in between. I flip it a whole number of times. I come up with an estimate, and then I have an estimate, and I'm more sure or less sure of it. It's not the truth. It's an estimate. Perhaps if I flip it more and more times, my estimate will become, on average, more and more accurate. At any point, I can stop. I have my best estimate in my hand. Let's say I flip the coin 3 times, and it landed on head once, and I decide that my estimate is 1/3. Probability of, let's say that the truth is 0.6. Not a very good estimate. I estimated 0.33. The truth is 0.6, but it's an estimate. Now I can stop my model learning and observe future flips of the coin and measure how surprised I am. I'm going to be quite surprised, maybe more than necessary, because my model is not very good, because my Q is not very close to the true P. But if I flip the coin 1,000 times and then created an estimate, hopefully that estimate will be a lot closer. Maybe it will be not 0.6, but 0.61. Now P remains 0.6. Q is 0.61. The cross entropy from 0.6 to 0.61 is much closer to the true entropy, which is the same as cross entropy from 0.6 to 0.6. So I made progress, and I can measure that progress by how surprised I am by future events. Okay, what are the units of entropy? Bits, right? Entropy is a special case of cross-entropy. And what is the possible range of values for entropy? Can it be negative? No, it's a special case of cross-entropy, and cross-entropy cannot be negative. Can it be 0? Can you give me an example of a distribution P with entropy 0?
Just a constant.
A constant function. Okay, slightly more general way of saying it is, of all the events in the space, one of them will happen with probability 1 and the others will never happen with probability 0. That's the only case where entropy can be 0. So this is if and only if Pi equals 1 and P of j not equal I equals 0. So this is a fancy way of saying it's the degenerate distribution. Always the same thing. So there's no uncertainty. You know what will happen every time. What about an upper bound? Can it be infinity? What did we say here? Here we said it could be infinity. Cross-entropy could be infinity. Can entropy be infinity? No, why not? Right, because it required this condition that there would be some event, P of this event should be positive, but Q of this event should be 0. But since P and Q are the same now, that is not going to happen. So for discrete sets of outcomes, which is all we're talking about here, right? Information theory can be generalized to continuous spaces, but we're talking about discrete spaces here. For a discrete space of outcomes, in fact a finite space of outcomes, this cannot be infinity. Let's say the set of possible outcomes is of size k. So the k possible outcomes. What is the largest value that the entropy can attain? Let's say there are two possible outcomes. It's flipping of a coin. What is the highest entropy we can attain? It will happen when the coin is fair. It's a uniform distribution over the k output, and therefore it'll be log k bits. And this equality is if and only if it's a uniform distribution. Namely, Pi equals 1 over k for every I. So for finite outcome spaces or event spaces, the highest entropy is achieved when the distribution is uniform. In that case, it's 1 over k for each outcome, and then no matter what happens, log of 1 over k is log of k, therefore the expectation of that is also log of k. So let's imagine a space of size k, k being 10, 20, 30, whatever, and all possible distributions over it. The distribution with the highest entropy is the uniform distribution, flat. The distribution with the least entropy, 0, is the opposite. All the probability mass is in one outcome and 0 everywhere else. So you can see that entropy, you can think of it as measuring the skewness of the space. It's maximal when it's uniform, when it's flat. It's also least informative, you can say. Has the most inherent uncertainty when it's uniform. And as soon as you deviate from uniform, even a little bit, entropy goes down. We can look at a special case of k equals 2. When k equals 2, we have only P1 and P2, and they sum to 1. So instead of calling them P1 and P2, I can call this guy P and call this guy 1 minus P. There's only one degree of freedom. And now I can calculate the entropy as a function of P, which is effectively a function of both of these things. P can take on values between 0 and 1. And for each one of these values, I can calculate the entropy. It corresponds to the probability of head, the entropy of probability of head being a particular value. Let me write down the explicit expression for entropy for this case of k equals 2, entropy of P1, P2, which I will also call entropy of P and 1 minus P. This is just a change of naming, just to emphasize the fact that that there's only a single degree of freedom here. Using the formula for entropy, which is right over here, you sum over all possible events the probability of the event times the information you get from that event. So this is P times log of 1 over P plus 1 minus P times log of 1 over 1 minus P. If you want, you can put P1 here and replace this with P2. The general case would be sum over I of Pi log of 1 over Pi. So now I can take this function, which is a function of a single variable, and plot it here. What would it look like? What would it be for P equals 0? 0. This corresponds to a coin that always returns tail. Probability of head is 0. Why would it be 0? Because we would have, if P equals 0, this part is easy to see. 1 minus 0 is 1. I'm sorry, which part is easy to see? Yeah, this part is easy to see. This is 1. 1 minus 0 is 1. 1 over 1 is 1. Log of 1 is 0. So do you have 1 times 0 here? So that's easy. What about this part? This is a little more complicated because P equals 0 is 0, but 1 over P is infinity. Log of infinity is infinity. Infinity times 0 is what? Undefined, right? So I claim infinity times 0 in this case is 0. And let me tell you why. Because you can define it as a limit of P times log 1 over P limit as P goes to 0. And the limit of this is 0. As you can do using L'Hopital's rule, take derivative or whatever. Intuitively, this part, this is like 0 times log of infinity. This is just intuition. Log of infinity goes to infinity more slowly than 0 goes to 0, right? So the log, because of the log, this wins. But you can just do the math and take the derivative and see that it goes to 0. So we're going to define P times log of 1 over P as 0 for P equals 0 because it is the limit for P going to 0. So that's 0 right here. So this is 1 point in our distribution. What about 1? What about a coin that always lands on head? What is the entropy of that coin? Also 0. Same thing happens, but in the opposite direction. This part is trivially 0. This part is 0 after you define the limit. It's the same limit, basically. As P goes to 1, 1 minus P goes to 0. All right. Where will this achieve its maximum? Equal probabilities, that's 0.5. What is the entropy of a fair coin? Well, P equals 0.5, so 1 minus P is also equals 0.5. So this is half times log of 2 Log of 2 is 1 bit, so half of 1 bit plus half of also 1 bit. So it's half times 1 plus half times 1 usually comes to 1. So this would be 1. Is this a continuous function? Is the entropy, in this case, a continuous function? You're supposed to know calculus. Of course it's a continuous function. It's not, it's well defined in the open interval between 0 and 1. So now we have to connect these with a continuous function. I'll save you the details, but it looks like this. Supposed to be symmetric. I don't know how to draw. Think about this as the master function for a coin. But it's not just a coin. A coin is just an example. In the real world, if you have a source of events, of binary events, yes or no, green or blue, whatever, if you have a source of events, and that source provides events with a true distribution that is equal, it is more informative, on average, than a source that provides information, that provides events that come from a skewed distribution, skewed in either direction. Are you guys familiar with the game 20 Questions? So it's a very, very simple children's game. Adults play it too. One person thinks of a category of movies or cities or anything you want. The other person is supposed to guess what they were thinking by asking them yes or no questions. If it's a movie, is it a comedy? No. Is it a documentary? Yes. So forth. And try to get that resolved in 20 questions. That means you're trying to extract information from that person, right? I used to play this game with my kids with numbers. I would guess a number between 1 and 100, and they would have to ask me, is it greater than 30 or lower than 30? I'm talking about when they were 4 or 5, learning their numbers and relations and so forth. When my daughter, then 4, was choosing a number between 1 and 100, I would ask her, is it greater than 50 or less than 50? And if she said it's less than 50, I would say, is it greater than 25, less than 25? Binary questions. That makes sense. When it was my daughter's turn to guess, she would ask me, is it greater than 10? 10 being a very big number in her mind. And I would say yes. And then she would ask, is it greater than 12? This is a real story. Now, what is funny about what she did? Why is cutting in the middle better than cutting at 12? Or even starting with 10? More information. So you're saying because it'll give more information. So what if the number I chose was 11? Then all of a sudden her strategy looks brilliant, right?
It's highly possible that you can only only 10
Right. So, you said two different things here. You said highly possible or probable, and the other is that eliminate a space. So let's think about it probabilistically. Yes, if I had chosen 11, then her questions would have been great. She would get to the truth faster than I would. But most of the time, I will not choose 11, right? So the critical point is, what is the expectation about her expectation about my answer? She will get the most information if the expectation is that my answer is as likely to be yes as it is to be no. Because if a priori it's as likely to be yes as no, you're getting 1 bit of information. Whereas if a priori it's 95% chance of being yes and 5% chance of being no, then on average you're getting much less information. Now it's important to say it's on average, because if you remember, we're talking about a question, the answer to which is 95% of the time yes, and 5% of the time no. Versus one for which it's 50-50. I say ask this kind of question much better than asking this kind of question. Why? Because the amount of information that you will get on average is higher here than here. On average, this will give you this amount of information. In fact, it will always give you this amount of information. If it's indeed 50-50 chance it'll be yes or no. Whereas if you ask this kind of question, most of the time you will get extremely little information. Sometimes, 5% of the time, you'll get a lot of information. This corresponds to the case of her asking me, is it greater than 12? And I'm saying no, and then she knows it's 11. So she got lucky. Every now and then you will get lucky. But on average, you will be worse off. And this is what this formula tells us. Let's think how this formula applies to this average. 95% of the time, the amount of information you get is log of 1 over 0.95. This is very close to 1. So the log of this is very close to 0. So 95% of the time you get very little bits of information. 5% of the time, log of 1 over 0.05, this is 20. Log of 20 is more than 4 bits. So there's a large chance that you will get very little data and a very small chance you get a lot of data. And it's hard to tell a priori if this is better or worse than always getting 1. But I'm telling you from the formula that it is worse. That the weighted sum of this is here or here. Significantly less. So you want to ask questions, the answer to which it has the most uncertainty in them. And that's true for a 20-question game. It's true also when you're trying to reduce the uncertainty of y with some x's. The most informative x's might be the ones that are more or less uniformly distributed. Not necessarily. We're going to get to that in a minute. But as a first-order approximation, if you can choose from a lot of attributes in your data set, and you notice that some of the attributes have the same value 95% of the time, they are likely to be less informative. In fact, the amount of information in them is bounded by this formula. The opposite is not true. You could have an attribute that is distributed uniformly in your training data. Its values are distributed uniformly, and therefore, potentially it can give you a lot of information. It could still turn out that it gives you information about itself, but not about the outcome you're interested in. It could be completely uncorrelated with the answer. But the entropy of a variable by itself, any attribute or any piece of your input, the entropy of that variable is a upper bound on how much information you can possibly expect to get from it about the thing you care about. We will discuss that in more detail later. Let's go back to this side of the board, which is the side where we know the truth, P. And we can observe somebody who knows only Q and think what we think about them. So the truth is P, model is Q. I can think about the distance of the model from the truth. From the truth. I'll write it like this: distance. I'm actually going, even though I say of model from the truth, I'm actually going to look the other way around. I'm going to look at the distance from the truth to the model. The reason I do that is because I want to judge that distance relative to, by the true measure. So imagine the truth is here, and you stand on your model, Q, which is here. You look to the truth, and it looks really close, maybe. But if I stand on the truth and look at your model, you don't look so close to me. I care about what the person who stands at the truth sees. Okay? I care about the view from the truth of how far you are from me. So, of course, in a regular world with a regular distance measure, it doesn't matter, they're symmetric. But the distance measure that I'm going to show you here is not true distance. It's not symmetric. So it's important from where to where. So this is the distance as viewed from the truth towards the model. I will also write it like this, distance from P to Q with two vertical bars. Am I going to define it as the cross entropy from P to Q minus the entropy of P? To remind you, this is the average uncertainty, expected uncertainty of modeler Q when they observe events from P. And this is the irreducible uncertainty of P. The best that anybody can do if they knew P. The difference between them is the degree to which the model is imperfect. It measures the imperfection of the model. You can think about it as dividing the uncertainty into two parts. One part due to the incorrectness of the model, the fact that Q is not exactly P. And the other part is due to the inherent uncertainty of the process that is irreducible. This is irreducible. This is the error or inaccuracy. So what we're saying here is that the cross entropy, your current uncertainty, and this is the irreducible uncertainty. We measure our level of imperfection, or imperfection of the model, three different terms for the same thing, as the difference between our current level of uncertainty and the minimum possible, minimum achievable level of uncertainty, that gap. Now I can open up these by their definitions. This is a summation over all event types of the probability of E. Here it's times log of 1 over Q of E minus another summation, probability of E times log of 1 over P of E. I'll write it again here in a slightly simplified form. Sum over E, P of E, times log of P of E over Q of E. And I can rewrite it again using notation of expectation. This is the expectation of the log of the ratio of P of E to Q of E. And this expectation is with regard to P. This is always important when you write expectation to know its expectation with regard to what distribution. So I go over all possible outcomes. I look at the ratio of the true probability to the presumed or model probability, take the log of that, and take the expectation over all events. This is measured in bits, like everything else. Could it be 0? When will it be 0? I'll take this general mumble to mean when p equals q, right? Or rather when q equals p. When q equals p, this is 1, log of 1 is 0 for all of them. In fact, it's the only time when it would be 0. If you remember our fundamental equation over there, this must be greater than this if there's even a slightest difference between p and q on anything. So this is greater or equal 0. Can it be infinity? Can it blow up? Yep, yeah, I see agreement. Yes, it could be infinity. When will that happen? Same time when this becomes infinity. Remember, this is finite, always, between 0 and log k. This could be infinity. When does that happen? When there's at least one event for which the model says it can't happen, but the truth is it can. It goes without saying, but I'll say it anyway, that d of p to q is not the same as d of q to p. So if you swap their roles, if q is now the truth and p is, then it's not the same value. One of them might blow up, the other one might not blow up. So it's not symmetric. And it also, it's not symmetric, and d of p and q is 0 if and only if p equals q. I think I need to let you go, so we'll continue next time. Thank you.